all over again.
For sure.
I set up everything except for I forgot to click on unmute. Okay, so
all right,
so let me explain.
So you were talking, I was like, that's weird. Like she's like making lines and all that, but he doesn't even have his mic like on.
That's right. I don't
Maybe
my one little small technical problem. There was one small technical problem with this. So.
It's fine.
Okay. Thank you for telling me.
For sure.
Yeah, and one of the things that you do notice is that unfortunately, when I'm doing a screen share, I have to go back to the Zoom to look at the chat. So unfortunately, I didn't see that people were saying we can't hear you. So yeah, so if somehow I don't respond to you, it's because from the chat is that I can't see the chat until I go back into Zoom. Okay, so let me tell you how this workshop will be run.
Right.
So what we will do here is I have some prepared material here, and I'll go over it. But if there are any questions throughout this, just ask me, and I'll respond to you. And of course, if I don't respond to you, turn your mic on and then tell me so that I can know that you're asking me something. This sample exam that I prepared here is actually a superset of your exam. I've looked over all the questions, and I've asked other instructors their questions that they're asking. And so these are all types of questions that could be asked on your first exam, but they're more than will actually be asked on your exam. So there'll be more questions than what will be on your exam, because some instructors may not, give one or two of these questions. So when I say they're the same questions as on your exam, well, modulo some things, such as maybe the numbers are changed, or maybe there may be some additional words that have been added to the question that may not be on your particular version of the question, or maybe the question is the same type of question, but rather than saying car owners, they say dog owners or something. So it'll be the same type, but maybe they've slightly reworded the question, but it's the same type of question. And so it's the same question in the same vein. So I will give you every possible type of question that you might see on your exam. So as I said, you're going to actually see a little bit more than what will be probably on your exam. But that's okay. At least I'm showing you everything. If you wish to see additional things, then just stop me during the workshop and ask me, and I will do them. And towards the end, after I'm through with all this, then just ask me additional questions, especially at the end, and I'll do additional questions if we have time. Okay. Oh, and of course, after a few minutes, I will also check in students through Pinji so that the math lab gets money. Okay, so for attendance. So, okay. Exam number 1, Math 227. Problem number 1. Suppose that the annual expected mortality rate from lung cancer is 182 per 100,000 individuals in a specific community of 508,840 individuals. How many deaths are expected to be attributed to lung cancer over a 1-year period? Use the California method round your answer to the nearest whole number. So let's do that. So let's just multiply the 508,840 times the rates, the annual rate. So you expect that in 1 year, 182 out of 100,000 will get lung cancer. And so let's multiply 508,840 times 182 over 100,000. And so if you multiply these together on your calculator, you get 926,08880. Divide that by 100,000. And so you get 926.0888. Rounding to the nearest whole number. Well, this is next digit here is 0. So we'll round it to 926. Problem number 2. On a test, 56% of the questions are answered correctly. If 50 questions are correct, use the California method to determine how many questions are on the test. Round to the nearest whole number. Okay, so it's similar to the previous question, but there's a slight little subtlety. So the number correct is, well, how many questions are on the exam times the percent that you got correct, written as a decimal. And so we have 50 questions that are correct. I don't know how many questions are on the exam, so I'll just leave that as n. And I have here that 56% were answered correctly. So let's solve for n. So let's divide both sides of my equation by 0.56. And so n is just equal to 50 over 0.56. You can reduce this. It really doesn't matter. This step is unnecessary. But on your TI-83, well, on most calculators, it's easy to see the reduced fraction. And so 50 divided by 56 is 625 over 7, or you can skip to this step. 50 divided by 0.56 on your calculator is 89.285714285714. So let's round this to the nearest whole number. So, well, the digit here is the next digit, the 10th digit is a 2. Therefore, I'll round this to 89. So there were 89 questions on the test.
Sir, I have a question.
Question, yes.
Okay, so if we were multiplicating, what would we get, like, instead of dividing? The answer we're gonna get?
But think about this.
Mm-hmm.
So if you multiply these two numbers together, then that would say that there were 50 questions on your exam. You got 56% of them correct. How many did you get correct? You'd only have 28 or something correct.
Yes.
But that's not how many. Then think about it. Now let's think for a second. It says how many questions were on the test. You're saying there are 28 questions on the test and you got 50 correct. How is that possible? Mm-hmm. How is it that you got 50 questions correct on a test that only had 28 questions?
Mm-hmm.
Then you think to yourself, oh, I did it wrong.
Mm-hmm.
This isn't the number of questions on the exam. This is how many I got correct. So it's a division problem, right? You want more questions. Obviously, there are more. You want more questions on the test than there are ones that you got correct. right? The other way around is impossible. You can't have more questions correct than questions on the exam.
Okay.
Okay.
Mhm.
Okay, then. Problem number 3. A study was conducted of all 1,134 car owners in a certain country. The average age of the owners is calculated. Determine whether the average age of the owners is a statistic or a parameter. So they're trying to trick you. Okay. So students here see 1,134, and they automatically say, oh, that's a small number. It's a statistic. Wrong. All in a country. So they're talking about every person. It's a really small country. So we're talking like Vatican City or something. We're talking because there are only 1,000 cars in the whole country. So there's only 1,134 cars in the whole country. And they have asked every one of these 1,134. Therefore, the value is a parameter because it is a numerical measurement describing some characteristic of the population. So these 1,134 people, car owners, are the whole population. It's the whole population of that country. It is when I say population, meaning the number of car owners. So our population, the set that we are interested in studying, are car owners in this country. The total number of car owners in this country is this amount. This is not a sample. It is the whole, it's a census of the whole country. It is a parameter. Okay. So be careful. Just because it's a small number doesn't mean it's a statistic. Just because it's a large number doesn't mean it's a parameter. You have to see what this number corresponds to. Does it correspond to a census, everyone in the country, or does it correspond to a subset of the country, of the population? Problem number 4. The weight of Bill's pack as he sets off on a backpacking trip is 48 pounds. Does the data come from a discrete or a continuous data set? Weight is calculated by measuring. You measure the weight of his backpack. And so you're measuring a weight of a pack. Since you are measuring, it is continuous. And so if you were counting, it would be discrete. If somehow you have to have some instrument to measure a weight, you put it on a scale, then it is continuous. So there's some instrument that you use to measure this particular random variable. So it is a continuous data set because there are infinitely many possible values, and those values can be measured or are being measured. And so these are being measured. 5. Oh, this is going to be, so problem number 5, critic ratings of movies on a scale from 0 stars to 5 stars. Which level of measurement is most appropriate for this data? And so this is ordered from 0 stars to 5 stars. So this rating is somehow ordered. Therefore, I know not only how many stars it has, what set it's in, I also have a total ordering on that set. Therefore, this is an ordinal level of measurement. Just have to remember the terminology for levels of measurement. Six, to determine customer opinion of their safety features, Toyota randomly selects 140 dealerships during a certain week and surveys all customers visiting the dealerships. Identify the type of sampling used. Well, because they're picking the dealerships randomly, then it is a random sample. And so they are concerned with customer opinions about their safety features for each of the dealerships across maybe a country or whatever. And so they randomly choose 140 of them. Therefore, this is a random sample. 7. An ad for seatbelts claimed that proper usage of seatbelt reduces the chance of fatality in a certain car crash by 400%. What is wrong with this statement? Okay, so obviously, this is actually a multiple choice question. So, of course, I'm just writing down the answer, the correct multiple choice answer. So, you are reducing by 400%. Notice that if you reduce the number of fatalities by 100%, they've gone down to 0. Well, you can't reduce it any more than 0. I mean, once you have 0 fatalities, that's it. You can't have like a negative fatality or something. You can't get below 0 fatalities. Therefore, you can't get more than 100%. So it's impossible to get more than 100%. You can't certainly have 400%. So if seatbelts eliminated all fatalities, it would result in 100% reduction. So it's not possible to reduce fatalities by more than 100%. So their statement that they've reduced it by 400% cannot be correct. It makes no sense at all. Problem number 8. Quiz scores of statistics students were obtained by a teacher and listed below. Construct a group frequency distribution beginning with a lower class limit of 0 and use a class with a 2. What frequency is listed for the 4th class? And so I have here 1, 5, 5, 5, 3, 7, 9, 2, 5, 10. Even though they're only asking you for the frequency of the 4th class, you must construct the complete group frequency distribution. So first off, we have here a lower class limit of 0 and a class with a 2. So my first class goes from 0 to 2. And the largest number here is 10. So I'm going to keep going until I get to 10. So my classes are 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. These each have class widths of 2. And now let's, well, I guess I'll go this way. Let's try to figure out how many numbers are between 0 and 2. Only one number is between 0 and 2. How many are between 2 and 4? Well, there's 1, 2 number between 2 and 4. Between 4 and 6, 1, 2, 3, 4. There are 4 numbers between 4 and 6. Between 6 and 8, just 1. Between 8 and 10, 2. There are 2 numbers between 8 and 10. And so I want to find the frequency of the 4th class. 1, 2, 3. Here's the 4th class. The frequency for the 4th class is 1. Okay. Problem number 9. In a survey, 26 voters were asked their ages. The results are shown below. Construct a group frequency polygon to represent the data with 5 classes, beginning with a first class mark of 25 and a class width of 10. What is the lower class limit of the second class? Okay, so let's do this. Again, you have to construct your group frequency polygon. You don't only answer this question, even though that's what you would, even though this is what you would input into your computer. We are grading this and this. Okay, so we have 5 classes. So the first class mark is 25. Oh, I didn't do. And so here are all the numbers. Here are the numbers. 44, 50, 56, 40, 33, 56, 20, 44, 25, 36, 28, 43, 63, 40, 66, 33, 47, 34, 47, 52, 50, 43, 46, 50, 25, 28, 38. Okay, so let's construct a group frequency distribution. So I have the following class mark. So the first one is 10. And the class width, I'm sorry, the first class mark is 25 and the class width is 10. So I have 25 to 35, because that's a class width of 10, to 45, to 55, to 65, because we want 1, 2, 3, 4, 5 classes. And so the class width here is 10. The class mark is 25, so it's in the middle. And so if the class width is 10 here, that means you go 5 above and 5 below. So you go from 20 to 30. And that's your class. Same for this. The class mark is 35. The class width is 10. Therefore, you're going from 30 to 40, 40 to 50, 50 to 60, 60 to 70. There are how many numbers between 20 and 30? 1, 2, 3, 4. Oh, between 20 and 30, you jerk. 1, 2, 3, 4, 5. There are 5 numbers. 1, 2, 3, 4, 5 numbers between 20 and 30. There are 5 numbers in the 20s. How many in the 30s? And so there are 1, 2, 3, 4, 5 numbers in the 30s. So 1, 2, 3, 4, 5. There are 5 numbers in the 30s. How many numbers in the 40s? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 numbers in the 40s. How many numbers in the 50s? Let's switch this over. How many numbers in the 50s? There is 1, 2, 3. Here. 4. So 1, 2, 3, 4, 5 numbers in the 50s. How many in the 60s? There are 1, 2, that's it. So there are 2 numbers in the 60s. And so now let's draw the frequency polygon. So I have here at 25, I guess I have to move over here. So at 25, there are 5 numbers. So at 25, I'll do 5. At 35, there's 5. 45 is 9. At 55, there's 5. At 65, there's 2. And so let's draw a line connecting these, and let's anchor. And so if I anchor, my group frequency polygon should look something like this. And we have that the lower class limit of the second class is 30. Any questions about this? This is a longer one. Okay.
Yeah.
Question. Any questions about this? Nope. Okay. Let me do problem number 10. Subscribers of the women's magazine, Cosmopolitan, are asked to participate in a survey about preferred cereals for breakfast. Are the results likely to be representative of all women, of all subscribers of Cosmopolitan? Why or why not? And so, well, are they likely to be representative of all women? Well, no. So because the participants self-select themselves to be participants in a survey, and because only subscribers of Cosmopolitan are asked to participate in the survey, it's unlikely that subscribers to Cosmopolitan are representative of all women in the country. And so then the results are unlikely to be representative of all women. It is unlikely that a subscriber for Cosmopolitan is representative of all women. In fact, since these participants self-select themselves to take the survey, it is unlikely that this will be representative of all subscribers of Cosmopolitan. So it's neither representative of all women nor of all subscribers to Cosmopolitan. Any questions about that? So it really has 2 problems here of trying to be representative of women. One is that you're only asking subscribers of one magazine. And so that's unlikely to be representative of women. And you're doing this so that they self-select themselves to participate in the survey. And so that makes it even less representative of all women. It does not even make it representative of the subscribers of the magazine. Any questions about that? So no, this is not representative of women, nor is it representative of subscribers. 11. The weights in pounds of 6 dogs are listed below. Find the root mean square of their weight. Round your answer to one more decimal place than is present in the original data. Okay, so we have here 10.2, 9.2, 3.6, 12.6, 13.6, 12.0. So they're asking for a root mean square. Well, let's look up the formula for a root mean square. So the formula for a root mean square is, it is the square root of the sum of the square of the data values divided by how many data values there are. So let's just take 10.2, square it, add it to 9.2 squared plus 3.6 squared plus 12.6 squared plus 13.6 squared plus 12.0 squared. Add those all up. You will get 689.36. And there are 1, 2, 3, 4, 5, 6 data values. So divide by 6 and then take the square root. So 689.36 divided by 6, 114.8933. Take the square root of that. 10.71883078. Then they say round to one more decimal place than the data. The data goes one decimal place. Therefore, you want to round this to 2 decimal places. And so 8 here is greater than or equal to 5. So I'll add 1 to the 1 to get a 2. So 10.72. Any questions about that? So you just, yes, question.
Yes. So the formula
Yes.
is a total of all the amounts to the square root to the
No. You square each of them. So meaning you square each of them. Add them up. Divide by 6, and then take the square root. So you square each of them, add them up, divide by 6, then take the square root. And that gives you this number.
Got it. Thank you.
Okay, good. Any other questions about that? Okay. Oops. 12. Andrew asked 8 of his friends how many cousins they had. The results are listed below. Find the median number of cousins. Round your answer to one more decimal place than is present in the original data values. Use Excel old version method. Okay, so let's do this. We have here 5, 13, 12, 10, 14, 1, 0, and 10 cousins. So let's find the median. So the first thing to do is, let me write down Excel old version method, which says you add 1 to n, multiply, in this case, by half, and then you write your position as an I, the integer part, plus f, the fractional part. If the fractional part is less than 0.5, it's just x sub I. If it's equal to 0.5, then you add xi and xi plus 1 and divide by 2. If it's greater than 0.5, you take x sub I plus 1. Meaning, well, so now let's sort the data. And so 0, 1, 5. So 0, 1, 5. 10, 10, 12, 13, 14. So 10, 10, 12, 13, 14. So there are 1, 2, 3, 4, 5, 6, 7, 8 numbers. And so 8 plus 1. So you look here, where's the median going to be? There's 4 below, 4 above. It's going to be right in the middle here. And if it's in between, that means average those two. So let's do the calculation. So it says you take, there's 8 numbers, add 1 to that, and divide by 2. So 4.5. And so x sub I, and so I, the integer part of the position function, is 4, and f, the fractional part of this position function, is 0.5. Therefore, it's going to be the average of the 2 middle guys. And so it's the average of the number in the 4th position plus a number in the 5th position. And so you want to take the average of 10 and 10, which is 10. So Excel, old version, just says, well, if your median is in the middle, then you just take the average of the 2 middle numbers. And that is your median. Any questions about this? Okay. 13. Find the mode for the given sample data. If there are more than one, enter the largest value for credit. If there is no mode, enter 0 for credit. These are just instructions that you get on the computer. So 10, 4, 8, 9, 1, 6, 8. So if I look here, well, let's see. All these numbers, except for 8, only appear once. 8 appears twice. Therefore, the mode, which is the most frequent, is the number 8 because it occurs most often. And so that's the mode. 14. The normal monthly the normal monthly precipitation in inches for August is listed for 10 different US cities. Find the standard deviation of the monthly precipitation. Round your answer to one more decimal place than is present in the original data. So 0, 3.3, 5.6, 5.5, 3.6, 3.7, 1.3, 3.3, 4.6, 1.4. So let's find the standard deviation. I guess I'll find the variance first because I don't have to, and then I'll take the square root. So it's easier to, at least notationally, not have to put the square root each time I do the calculation. So let's find the sample variance. And so the sample variance is the sum of the squared deviations from the mean, sample mean, divided by your degrees of freedom. Or we also have a simplifying computational formula that the sample variance is n times the sum of x squared times the sum of x over n times n minus 1. So to find the sum of x, you would just add up all the data values. On your calculator. And you would get 32.3. Next, you would square every data value and add them up. So just square every data value, add them up, and let's see what we get. Plus 3.3 squared, plus 4.6 squared, plus 1.4 squared. So if you square every data value and add them up, you get 134.85. Okay, and so to evaluate the sample variance, the sample standard deviation, I want to add up all the data values, getting 32.3. I want to square every data value, add them up, getting 134.85. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So n is 10. The sum of x squared is 134.85. The sum of x is 32.3. Square that. N is 10. N minus 1 is 9. And so you get 10 times 134.85, 1,348.5. Subtract from that 32.3 squared to get 305.21. 10 times 9 is 90. Divide these. So you get 3.39122. So to find the sample standard deviation, you take the square root of this variance. So the sample standard deviation is the square root of 3.3912222. And you get on your calculator 1.841527144. And now we want one more decimal place than is present. Well, what's present is to the 10th decimal place. Therefore, I want to round to the 100th decimal place. Well, 1 is less than 5, and so I just get 1.84. Any questions about that? So there's a little bit of calculation here. Of course, you could all do it on your TI-84. And actually, that's what I did, is I just then input the data into the calculator and read off these values from the calculator.
Are the formulas going to be written out on the
Yes.
test? Or okay, great.
Well, not on. They won't be written out on the test. You will be given a formula. Well, it's not a formula sheet. It's a formula package. It's a gigantic. It is basically every formula that you've been given throughout the course. So we always attach all formulas to your exam in statistics. So in statistics, all the formulas, so you don't have to memorize. So all this stuff, whatever, that's all this stuff here, et cetera, you don't have to memorize any of that. All you have to be able to do is plug into formula using calculator. And that's really it. Okay.
Thank you.
So the answer is no, you don't have to memorize these types of formulas. You don't have to memorize any type of formula actually for statistics. All you need to do is look it up. I mean, the hardest part for students is looking it up and then try to figure out which formula to use. But as far as do you have to memorize any of the formulas? No, you do not have to memorize any formula. All the formulas are given to you, and that's all. And that's because also in the very near future, there's going to be a whole bunch of tables that you'll be given. And so we'll also give you tables, not in this test, but in, the chapter 2 and above, the second exam and third exam and the final. You also have tables that will be given to you. Okay, so problem 15. Oh, I should do that at this moment. Let me do this at this moment before I forget about it. Where do I go? Wait 1 second. It's got to be here. Aha, check in students. Okay, so let me ask you, Anna, are you here?
Yes, sir.
There you go. Okay, so check in. Checked in. Merlin, are you here? Mackenzie, are you here? Nathan?
Yeah.
Okay. Wendy?
Yes, I'm here.
Okay. Good.
Thank you.
Okay. Anyone who I did not ask? Is anyone here that didn't sign in? Oh, good. That's good. So I think okay. I don't know if I'm supposed to do that. At the end, I'll do that. Okay. Oops. Okay. So no one else was here. So I called everyone's name. Okay, good. Problem number 15. The manager of a bank recorded the amount of time each customer spent waiting in line during peak business hours one Monday. The grouped frequency distribution below summarizes the results. Find the standard deviation of the group frequency distribution. Round your answer to one more decimal than is present in the original data values. So waiting times in minutes and number of customers. 0 to 4, 12. So 12 between 0 and 4, 7 between 4 and 8, 2 between 8 and 12, 6 between 12 and 16, 4 between 16 and 20, 8 between 20 and 24. And so I want to find the standard deviation. Okay, so let's do that. Let's find the standard deviation of this. So I'm going to have to rewrite this again. Maybe I'll go like this.
Excuse me, I had a question.
Yes.
I remember in like what were the waiting time limits, but like the class limits, like the 0 to 4. I remember there was a homework I did recently, and everything like went down by like, say like for this one, it went down by like 4, and then there was one limit that was like only by 1, but everything else was like had a limit of 11. But then there was one that had like there was a limit of 1 in between.
Oh, you mean the unequal class widths?
I'm sorry.
Unequal class widths?
Yes.
Okay. That actually wouldn't change anything because we're going to be looking at class marks.
Got it.
So we're looking at class marks. So the fact that, you know, this is a class width of 4 or whatever, it doesn't matter. I'm doing a class mark. So so in this case, I guess they're all equal, but it really wouldn't matter because you're looking at the class marks. Okay.
Right. Awesome. Thank you.
Okay, then. So let me collect all this data. And so I can find the standard deviation. And so the 0 to 4, there are going to be 12 between 0 and 4. Since I'm doing the standard deviation, I don't want 0 to 4. I want the class marks. I want what is the best point estimate? What's the best one point that represents the value for the whole class? Well, it's the class midpoint. It is the class mark. So the best one representative, one number that best represents all the numbers in this class is the one number in the middle, the class mark. So I have here, well, what's the average of 0 and 4? 2. And again, the frequency was 12. Let's do, well, for 4 to 8, the class mark is 6. 4 plus 8 is 12, divided by 2 is 6. And the corresponding frequency was 7. From 8 to 12, the class mark, well, 8 plus 12 is 20, divided by 2 is 10. And the corresponding frequency was 2. The class mark for 12 to 16 is 14, and the frequency is 6. Class mark for 16 to 20 is 18, class mark, and the corresponding frequency is 4. The class mark for the class 20 to 24 is 22, and the frequency is 8. So now, let's switch over.
A question, sir.
Yes, question.
Class mark. How you get the class mark?
It's the average.
Oh, okay, yeah.
So like, let's say for this guy, you just do 16 plus 20, 36 divided by 2. So it's the guy in the middle. It's whatever,
okay.
it's, right? Okay.
Uh-huh.
So now, let's attach 2 additional columns. The frequency times the class mark, and then the frequency times the square of the class mark. So to determine the 1, 2, 3, the 4th column, multiply the 2nd and 3rd columns. 2 times 12, 24. 6 times 7, 42. 10 times 2, 20. 14 times 6, 84. 18 times 4, 72. 22 times 8, 176. To determine this 5th column, multiply the 2nd and the 4th column. And so 2 times 24, 48. 6 times 42, 252. 10 times 20, 200. 14 times 84, 1176. Ooh, 18 times 72, is, yes, it is 36 squared. 1296. 22 times 176. Yes, it is 3872. Now, let's add up each of these columns. And so 12 plus 7 plus 2 plus 6 plus 4 plus 8. So that's 10, 20, 39. 24 plus 42 plus 20 plus 84 plus 72 plus 176 for 18. 48 plus 252 plus 200 plus 1176 plus 1296 plus 3872, 6844. And now plug into the formula for the sample variance. And then take the square root to get your sample standard deviation. So S squared is n, which is the sum of the frequency column, 39 times the sum of f times x sub cm squared, the 6844, minus the sum of f of x sub cm, 418 squared, divided by n, oh, we already found that, 39 times n minus 1, 38. So if you multiply these together, 39 times 6844 minus the 418 squared gives us 92,192. 39 times 38, 1482. And so divide 62.207.82726, and then take the square root. So if you take the square root of that, you get 7.887193.877. And then how do you, it says one more decimal place. Oh, everything here are whole numbers. So to the nearest, to the 10th. So let's round to the 10th, 7.9. Any questions about this? There's a lot of little calculations going on here, but nothing difficult. Any questions? Here, let me pull it this way. Any questions on this?
Professor,
Yes.
for this one, it's only when it's asking for the frequency, distribution. Because the other one that we did prior to this one is just the standard deviation.
Yeah. So the only difference, this is a group frequency distribution. So the only difference is like this F here, and for grouped, the class marks. But the formula really is, notice, the formula is the same. If you put an F here, and that would be for a frequency distribution. If you then also put the class marks here, voila, it's the formula for, so this is for raw data. So this is my formula here for raw data.
Okay.
No
So
F.
Okay, so
Right.
only use the other one when it's asking for the frequency.
Yep. In other words, it says frequency. And then
Okay.
you say, oh, frequency is what? F.
F.
So the F.
Okay, the F. Okay.
Right. So the F. And so if you hear frequency, then you know there should be an F there.
Okay.
Now, for if it's has a class or a group frequency distribution, well, then it's a whole bunch of numbers.
Yeah.
And obviously you can't plug in, the interval 4 to 8. So they just change it by, they give you the class mark.
Okay.
So that's the formula that involves the class mark.
Okay.
Okay.
Thank you.
Because you have to multiply numbers together. And so they have to give us a representative for these classes. And the best representative is the class marks.
Okay,
Okay.
thank you.
Okay then. And that was that. Okay. 16. Problem number 16. The mean height of a basketball team is 6.4 feet with a standard deviation of 1.5 feet. The team center is 6.5 feet tall. Find the center's z-score. And so the z-score is defined as x minus mu over sigma. It is x, 6.5, minus mu, the average, the mean, 6.4, over sigma, the standard deviation, 1.5. So just subtract. And so you get 0.1 divided by 1.5. And so that's, well, 2 over 30. And so you get 0.0666. And, oh, they don't tell you how to round. They should, we should tell you how to round. So round, oh yes, okay. Round to one more decimal. Then the data. The data in this case meaning the mean instead of. Okay, so we have this. So you should round to, so each of these are due to the nearest tenth. So let's round to the nearest hundredth. So let's round this to nearest hundredth. 6 is greater than or equal to 5. So let's add 1 to the 6 to get a 7. So I round this to 0.07. And so the center is 0.07 standard deviations above the mean of the team's height. Any questions about that? Okay. 17. Actually, it's the same question. Oh, here they tell you, good. A weight of 196 pounds among a population having a mean weight of 148 pounds and a standard deviation of 11 pounds. Determine if the value is unusual. Explain. Enter the number that is being interpreted to arrive at your conclusion, rounded to the nearest hundredth. So we want to determine if some value, 196, is unusual. Meaning, is 196 unusual given that the mean is 148 and the standard deviation is 11? Meaning, how many standard deviations above the mean is this value? Or how many standard deviations away from the mean is this value? Meaning, what is my z-score? So I want to calculate my z-score. So this is the number that I want to calculate. So z is x minus mu over sigma. Let me move this. And so x, 196, mu, 148 over sigma, 11. And so, oh, 4, that's big. Okay, so I get here 48 over 11 4.36363636. It says to round to the nearest hundredth. And so 3 is less than 5. So let's just drop that. Truncate the number here at the hundredth. So Z is 4.36. Well, you're greater than 4 standard deviations above the mean. And so that's like 99.999 percent of your data values will have values less than that. So this is very, very unusual. So 2 standard deviations above the mean is unlikely. Whereas 4.36 standard deviations above the mean is very unlikely, is highly unlikely. You never see it. I mean, you hardly ever see this. So that's just very, very unlikely to see. Okay. So is this unusual? Yes, this is highly unusual. Any questions about this? So in this case, they really didn't even tell you what to do. You had to figure out what to do. In this case, since they're asking you if things are likely or unlikely, they're really asking you, what is the Z value? The Z value will tell you if this is likely or unlikely. A Z value between plus or minus 2 is, well, likely. A Z value greater than, in absolute value, greater than 2 is unlikely. Problem 18. The weights in pounds of 16 newborn babies are listed below. Find Q sub 1. Use the empirical distribution function averaging method. Okay, so 6.3, 7.8, 5.5, 8.5, 7.4, 5.1, 8.7, 8.5, 8.5, 5.8, 5.2, 7, 7.3, 7.5, 7.1, 7.9. Okay, so first thing whenever finding any sort of quantile, sort your data. So let's sort my data. So let's sort this from smallest to largest. 5.1, 5.2, 5.5, 5.8, 6.3, 7, 7.1, 7.3, 7.5, 7.4, 7.5, 7.8, 7.9, 8.5, 8.5, 8.5. Oh, good grief. 8.7. And so I've sorted all of my data. Let me write down the empirical distribution function averaging method. So that's some formula given to you in your formula sheet. If this was given as a problem, they would give you that formula in your formula sheet. And so the position is given by n times p. Let's write p, let's write k as the integer part plus the fractional part. If the fractional part is 0, then we average. We take half of, well, we take x sub I plus 1 and divide by 2. If the fractional part is not 0, then we go to the next higher number. So let's do this. There are 1, 2, 3, 4, 5. Oh, actually, let's sort this way. 1, 2, count this way. 1, 2, 3, 4, 5. 8, 9, 10, 11, 12, 13, 14, 15, 16 numbers. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16 numbers. Good. So n is 16. We want to find the first quartile. So it's the first quarter, 25%. So 0.25. Now 16 divided by 4 is 4. And so there's no fractional part. Since there's no fractional part, then we're going to take the average of the number in the 4th and 5th position. So we're going to take the average of the number in the 4th and the number in the 5th position. So let's look for the number in the 4th, 1, 2, 3, 4, and 5th position. So I want to take the average of, I want to find what's in the middle of 5.8 and 6.3. Let's take the average of these. And so you take the average of 5.8 and 6.3. So let's add them. So 5.8 plus 6.3, 12.1 divided by 2 is 6.05. And so your first quartile is 6.05. Any questions about this? Okay. This may be topics that no one has covered yet. Okay, so let me do problem number 19. Find the percentile for the data value. Use the empirical distribution function averaging method. Round the answer to the nearest integer. So my data set is 2, 13, 7, 18, 4, 18, 19. The data value is 7. And so let's sort the data. 2, 4, 7, 13, 18, 18, 19. And let's look for the data value 7. It is the number in the 1, 2, the 3rd position. And there are 1, 2, 3, 4, 5, 6, 7. And so it is of 7 numbers, what fraction is 3 out of the 7 numbers? And so it's 3/7 of the way. So the empirical distribution function averaging method says, well, the position K, 3 in this case, this is it, the 7 is in the 3rd position, is N, which is 1, 2, 3, 4, 5, 6, 7. This 7 here is how many numbers are here. It has nothing to do with that number. That's a mere coincidence. There's 7 numbers. And so, and I want to figure out what P is. And so what percentile? So let's do 3 divided by 7. 0.42857, 142,857, 142,857, 142,857, etc. And so my percentile is 42.857, 142,857%. And I want to round to the nearest integer. So this is 43%. Oh, by the way, that was a question that someone asked. And so 7 is at the 43rd percentile. Now, of course, if they say round to the nearest integer, and they're talking about percentages, they don't mean this is 0.42, you round that to the nearest integer so you get 0. They don't mean that. They mean once you write it as a percent, then round to the nearest whole number. So 43%. Otherwise the answer is always going to be either 0 or 1, either 0% or 100%. So they don't mean that. What they mean what we mean when we say this is that you write your number as a percent and then you round it. Any questions about this? So the number 7 is 43% of the way from the beginning as compared to getting all the way to the end. Problem 20. Which is better? A score of 72 on a test with a mean of 78 and a standard deviation of 9, or a score of 273 on a test with a mean of 241 and a standard deviation of 25. Enter the better test score. So when comparing these, I want to compare differing values using, well, a z-score. Z is x minus mu over sigma. Let's calculate the z-score for both of these test scores. So let's see. Let me move this over. So I have here a 72 with a mean of 78 and a standard deviation of 9. So 72 minus 78, negative 6 over 9, negative 0.666. Let's now calculate the z-score for this. So 273 is my x, the mean, mu, 241, and sigma, 25. And so 32 over 25, 1.28. Well, 1 point here, notice, obviously this guy did better because he's above the mean, whereas this guy did worse because he's below the mean. So there's no way that this guy did better than this guy because he is below the mean, whereas he is above the mean. So I have here 1.28 is greater than a negative 0.66. Therefore, the score of 273 is better. Any questions about that? So it's similar to some other questions that were asked about a z-score. So here, you're just trying to figure out, well, which z-score is better? The one that has, well, which test is better? The one that has the higher z-score. 21. The test scores of 16 students are listed below. Construct a box plot for the data set using the empirical distribution function averaging method. Enter the maximum value. Okay, so we have here the following set of data. 27, 61, 25, 45, 86, 20, 28, 45, 60, 59, 11, 99, 46, 21, 86. So the first thing that we want to do here is sort my data. And so let's sort the data. And so 5, 11, 20, 21, 25, 27, 28, 40, 45, 46. 59, 60, 61, Ooh, big gap. 86, 86, 99. Okay, then that's it. Okay, good. So I've sorted my data. The empirical distribution function averaging method. K is equal to NP. You write K as the integer part plus the fractional part. And so I get that if the fractional part is 0, then the average x of I and x of I plus 1. If the fractional part f is not 0, then you just take the x of I plus 1. The box plot is really just a visualization of the 5-number summary. Smallest number, first, second, third quartiles, and the maximum number. So let's find the smallest number. That's easy, 5. So the smallest number is 5. Let's figure out the first quartile. There are 16 numbers, and we want the first quartile, so 1/4 of the way. 16 divided by 4 is 4. So I take the number. So in this case, I is 4, the integer part is 4, and the fractional part, f, is 0. That says when you have fractional part being 0, you want to take the average of, in this case, the 4th and 5th numbers. So you want to take the average of the 4th number and the 5th number. So let's find the average of 21 and 25. And so I'm taking the average here of the 4th and 5th number, the x of I number, and the x of I plus 1 number. And so the average of 21 and 25 is 23. So that's your first quartile. So that's the next number. Let's find the second quartile. So the second quartile, K is equal to N, 16. P, well, it's a quartile. And so second quartile, the median, it's halfway, the 50th percentile, 0.5. 16 divided by 2 is 8. Again, integer part is 8. The fractional part is 0. And so you want to take the average of the number in the 8th and the 9th position. And so 2, 4, 6, 8. The average of 40 and 45. So let's take the average of 40 and 45, 42.5. And that gives me my second quartile, the median. Let's find the third quartile. And so 16 times, well, the third quartile, that's 3/4. And so 16 times 3/4 is 12. So the integer part of 12 is 12. The fractional part of 12 is 0. So I want to find the average of the numbers in the 12th and the 13th position. And so 12 and 13. 2, 4, 6, 8, 10, 12. So I want to find the average of 60 and 61. So let's find the average of 60 and 61, 60.5. So my 5-number summary. The smallest number was 5. The first quartile we found was 23. The second quartile was 42.5. The third quartile, 60.5. The largest number, well, was 99. Let's calculate the interquartile range, the range of, the first and third quartiles. We're going from 23 to 60.5. So let's subtract 60.5 minus 23, 37.5. Let's see if there are any outliers. So first, let's see, are there any mild outliers? Are there any outliers? Am I more than 1.5 interquartile ranges from my middle 50% from these? So let's find if we're 1.5 interquartile ranges, so 1.5 times 37.5, 56.25. Are there any data values less than the first quartile minus 1.5 interquartile ranges? So 23 minus the 30, minus the, sorry, 23 minus the 56.25, negative 33.25. There are no numbers that are less than negative 33.25. There are no numbers that are less than like 5. And so certainly no mild or extreme outliers that are less than, that are small numbers. Let's see if there are any mild outliers that are big. So let's add to the third quartile 56. Let's add to the third quartile the 56.25. That's certainly going to be bigger than 99. And so I'll take the third quartile and add to it 1.5 interquartile ranges. So 60.5 plus 56.25, 116.75. Well, that's certainly much bigger than the largest number, 99. So there are no mild outliers. If there are no mild outliers, there's certainly no extreme outliers. So there are no outliers. So let's do a box plot where, you know, these whiskers go to the maximum minimum number. So let's construct my box plot. Let's put down my a number line. Let's do some tick marks. I'm going from 0 to 100. So these are nice tick marks. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And let's construct my box plot. Well, my minimum is 5. First quartile is 23. And the third quartile is 60.5. And so that gives me my box. The second quartile is at 42.5. So that gives me my dividing line. And I go all the way out to the maximum of 99. That gives me my other whisker. And so this is my visualization. Notice that this here is actually my 5-number summary. And we visualize a 5-number summary by looking at this box plot. And so, any questions about this? Okay. Problem 22. Prove the following. Let n be the population size. Do not use any other theorems to prove this. Only use the properties of summation. That the sum of all your data values is just n times the mean. Well, the sum of x is equal to, let me assume that my data, that n here is not equal to 0. Sorry. Let's assume that the population size is not 0. If the population size is 0, then of course this will be 0, but you're adding up nothing. And so that's also going to be 0. So let's assume that n is not 0. So let's just say assume that my population size is not 0. Then I can multiply and divide by n. But the sum of x over n is the mean. And that's what you wanted to show. So you're done. Any questions about this? Problem 23. Prove that for every k greater than 0, at least 1 minus 1 over k squared of the data lie within k standard deviations of the mean. Well, if sigma, the standard deviation, is 0, then x is always equal to mu for all x. Therefore, 100% of the data values are within k standard deviations of the mean for any k, because they're all equal to mu. So at least 1 minus 1 over k squared of the data lie within k standard deviations of the mean. So let's assume that sigma is not equal to 0, that the standard deviation is greater than 0. Let A be the following set, the set of all x's, such that the absolute value of x minus mu is greater than k sigma. Then let's look at sigma squared. Well, this is just equal to the sum of f x minus mu squared over n. So this is the sum of x minus mu squared times f over n. And let p of x equal f over n. Then this is equal to the sum x minus mu squared times p of x. Well, I'm adding this up. So for all x's, so I can add them up for x's in A and for x's that are not in A. So this is equal to the sum for x in A of x minus mu squared times p of x plus, well, the sum where x is not in A of x minus mu squared times p of x. Well, this is some non-negative number. This is some non-negative number. I'm adding up a whole bunch of non-negative numbers, and so this is non-negative. Therefore, this is greater than, actually, I should say greater than or equal to. What if these are all 0? Very unlikely, but. So this is greater than or equal to. Oh. There. So this is greater than or equal to the sum for x in A of x minus mu squared times p of x. Well, x minus mu in absolute value is greater than k sigma. Therefore, x minus mu squared is greater than k squared sigma squared. And so long as x here is in A. So I can replace this by saying, well, this, whatever is in here, is greater than the sum x in A of k squared sigma squared p of x. So let's bring this out. So this is equal to k squared sigma squared times the sum x for x in A of p of x. Let me rewrite this. So this is just k squared sigma squared times, well, the probability that x minus A in absolute value is greater than k sigma. Let's divide by k squared sigma squared. So I have that this is less than 0.22, less than or equal to 1 over k squared. Therefore, let's look at its complement. If the probability that x minus mu in absolute value is being greater than k sigma is less than, actually, that should have just said less than, because there was a less than in here. Yeah, there was a less than here. So this being less than 1 over k squared says that, well, the opposite. Well, what's the opposite? The complement. The probability that x minus mu, an absolute value, is less than or equal to k sigma is greater than or equal to 1 minus 1 over k squared. So this says at least 1 minus 1 over k squared of the data lie within k standard deviations of the mean. And that's what I wanted to show. So I'm done. This is Chevyshev's theorem. Problem 24. Use the true basic graphics toolkit method to compute the 83.755 percentile for the following set of data. Round your answer to 4 decimal places. 11.99, 3.49, 16.54, 9.73, 8.65, 7.56, 7.59, 8.32, 13.95, 8, 11.12, 13.35, 8.73, 17.26, 16.09, 14.54, 16.38, 13.9, 13.59, 10.28, 12.42. Okay, so first sort your data. And so let's try to sort the data. There's 8s, there's 3s. So the first one is 3, 7.56, 7.59, 8, a whole bunch of 8s. So 8 point. Oh, no, that's an 8.32. I'm sorry. That's not it. I'm sorry. That's an 8.32. So 8, 7.59, 8, 8.32. I saw the 8.65, 8.73, 9.73, 10.28, 11.12, 11.99, 12.42, 13.35, 13.59, 13.95, 14.52. There's 16s in there. 16.09, 16.54. Oops. 16.09, 16.38, 16.54, and did I miss anyone? 17.26, and that's it. Okay, good. So I sorted the data. So I've sorted my data here. So now let's do true basic graphics toolkit method. So the position K is equal to n minus 1p. And so the integer part, so I'll split this into an integer part and a fractional part. If the fractional part is 0, then we have x sub I. If the fractional part is not 0, then it's a linear interpolation, incorrect linear interpolation, very strange linear interpolation. It's x sub I times f, x sub I plus 1 times 1 minus f. So let's figure out there are how many numbers? There are 1, 2, 3, 4, 5, 6, 12, 13, 14, 15, 16, 17, 18, 19. There are 20 numbers. And so I have here, n is 20. So 20 minus 1 times, well, 0.83755. 15.91345. So the integer part, 15. The fractional part, 0.91345, which is not 0. So we'll use this formula. And so let's use the formula x sub I, in this case, x of 15 times f, the 0.9, well, the f. And then the next one, I plus 1, x of I plus 1 is x of 16 times 1 minus f. And so the 15th number, 1, 2, 3, 4, 5, 6. So 13.95, and the next one is 14.54. So I want to find the 15th number, 13.95, multiply it by f, the fractional part, 0.91345, plus the number in the 16th position, 14.54, times 1 minus the fractional part, 0.91345. Plug that into your calculator, you get 14.0010645. You want to round this to 4 decimal places. So 1, 2, 3, 4. Oh, 6 is greater than or equal to 5. So I'll add 1 to the 0. So 14.0011. Any questions about this? So again, this formula will be given to you on your formula sheet if this is a problem that you'll be given on your exam. Not everyone gives this problem on the exam. So if you're not given this problem on the exam, you obviously won't, problems of this type on your exam, you won't be given the formulas for it because it won't be given to you. 25. Use the closest observation to QN method in the linear interpolation formula to estimate the 23.78 percentile for the following group frequency distribution. Round the answer to 4 decimal places. So 1 number between 10-20, 7 between 20-30, 6 between 30-40, 6 between 40-50, 0 between 50-60, 6 between 16-70. So the linear interpolation method for the closest observation method, closest observation to QN method. Well, the position function for the closest observation method to QN is K is equal to NP plus 0.5, plus a half. Linear interpolation for a group frequency distribution is that your percentile is L plus H over F, K minus C. So let's do this. Let's create a cumulative frequency distribution. And so I have here, I can't quite see the first one. So the first one is, well, can't see it. So 10 to 20 is 1. So 10 to 20 is 1. Then after that, I can see the rest of them. So 10 to 20 is 1. 20 to 30 is 7. 30 to 40 is 6. 40 to 50 is 6. 50 to 60 is 0. 60 to 70 is 6. Okay, so now let's find the cumulative frequency. And so 1 plus 7, 8, plus 6, 14, plus 6, 20, plus 0, 20, plus 6, 26. Okay, good. So now, n in this case is 26. So let's figure out the position of the percentile. And so n is 26. My percentile is the 23.78 percentile. So 0.32378 and plus 0.5. You get 6.6828. Let's find the first time my cumulative frequency is greater than the 6.6828. Well, the first time is when the cumulative frequency is 8. Therefore, the lower class limit, this is our percentile class. The lower class limit of the percentile class, L, is 20. The class width of this percentile class, 30 minus 20 is 10. The frequency for the percentile class, F, is 7. The cumulative frequency for the class preceding the percentile class is 1. And K, we just figured out, 6.6828. Therefore, P is equal to L, 20, plus H over F, the 10 over the 7, plus K times K, 6.6828 minus C1. Plug that into your calculator, 28.11828.571. Now, we want to round to 4 decimal places. So 1, 2, 3, 4. 8 is greater than or equal to 5. So I'll add 1 to the 2 to get 3. So 28.1183. Any questions about that? Okay. Problem 26. John consulted with an accountant to prepare his tax return. He recommended the accountant to his friend, saying that this year, the amount he paid in taxes was 150% less than last year. What is wrong with this statement? Well, you can't reduce by 150%. If he paid no taxes this year, then his taxes would have been reduced by 100%. Thus, a reduction larger than 100% would be impossible. You can't pay less than 0 amount of taxes. So John could not have a reduction of 150% in his taxes paid. Oh, and that's it. So those were all the questions that I had from all versions of questions from any of the instructors that gave me questions, which are most of the instructors. And so this should be a superset of all possible questions that you could be, of all possible question types that you could be asked on your first exam. Any questions about anything? Any questions on anything? Well, we're 5 minutes early. So any questions? So I can ask. You can ask me anything. Any questions on anything? We have 5 more minutes left. Any questions on anything?
Is there a way we could keep this so we could look and study it over the weekend or something? For exam.
So yeah. So we will be posting the I will be, so the video of this will be posted, and I'll also send the PDF. So the answer is the video will be posted, and so will the PDF.
Thank you.
So everything that you hear plus everything that I wrote will be on, will be available through both. Well, if you're in my class, it'll be on my, on Canvas. It'll also be available through the math lab. So the math lab will also